A very common type of double replacement reaction is the precipitation reaction. These reactions involve mixing two soluble salts, such as sodium chloride, shown here with silver nitrate. These would both be clear solutions with the sodium and chloride ions completely dissolved and the silver and nitrate ions completely dissolved in the water. When you mix those two solutions, you get a precipitate of silver chloride as represented in this completed equation. That silver chloride, AgCl, precipitates out as a white solid, leaving the sodium nitrate remaining in the solution and fully dissolved. There are many videos on YouTube which you can look to see what this actually looks like when you mix the two solutions and form the white precipitate. So the solid, silver chloride, could have been predicted, and I'm going to show you a method for completing this reaction from reactants to products and then predicting that indeed silver chloride would have been a solid precipitate as a reactant. So let's predict if the above mixture will lead to formation of a precipitate. So let's say we don't know the outcome already. We're going to mix sodium chloride and silver nitrate. We want to know what's going to happen. The first thing you're going to do is to swap the ions in order to form the products in the reaction. So we're going to take the cations, the sodium and the silver, and switch their partners, the chloride and the nitrate. So we'll write sodium combined with the nitrate now, right? So we switch the cation and the anion there, and the silver and the chloride go together. Okay, these are the empirical formulas for those salts, sodium nitrate and silver chloride. They're complete. We can now determine if one of the products is insoluble. And for that, usually, until you gain enough experience, consult a solubility table. The rules in this table tell you what types of cations and anions will be soluble and in what combinations. The list is meant to be followed in order. So you read number 1, most alkali metal salts and ammonium salts are soluble. Well, sodium is an alkali metal, and therefore we can predict that a salt that involves sodium is going to be soluble. Furthermore, nitrates are also soluble, and that's very common. However, shown here, third line down, silver, lead, and mercury salts are insoluble, and therefore we would predict that the compound made of silver chloride is going to be insoluble, and so therefore we can complete the reaction and write in the states of both of those. Now you might notice that the next line, number 4, says that most chlorides, bromides, and iodides are soluble, and we have in fact formed silver chloride. However, the previous rule negates the next one down, so we ignore rule number 4. We actually don't even need to go down that far, because at number 3 we found that silver salts are insoluble, and therefore number 4 is negated. Number 4 we don't need to look to. It's negated by number 3. And of course this is the reason that silver nitrate, the original reactant, was also soluble, right? Because number 2 here shows that most nitrates, acetates and perchlates, are soluble. So that rule negates the next one down. In other words, silver is insoluble except when combined with nitrates, acetates, and perchlorates. So let's write those in, and that's the completed reaction. Let's predict the products for this double replacement reaction and write the balanced equation for the complete reaction. It is a mixture. We're forming a mixture of lithium hydroxide, which is soluble, as shown by the AQ behind the formula, empirical formula for that compound, plus lead nitrate, which is also soluble. When we mix those, we want to know if there might be a precipitate that is formed from these two salts. Remember, the first step is that we switch the partners, so we're going to switch the lithium and lead anion partners. So lithium now will be partnered up with the nitrate anion. Notice that since lithium is +1 and nitrate is -1, this represents the final and complete empirical formula for lithium nitrate. The plus and negative charges add to 0, and so we have a neutral compound, which is, of course, required. Plus, we switch the lead to partner up with the hydroxide. Now, in this case, lead is +2, and hydroxide is -1. And if you're unsure about the charge on lead, since it can have either a +2 or +4 charge commonly, look to the reactant. Nitrate is -1, and there are 2 of those, so that's a total charge of -2 for the anions in this empirical formula. And then that means that lead, in order to balance that, must be +2. So since lead is +2 and hydroxide is -1, we need 2 hydroxides for every lead cation. And so these are the empirical formulas for the correct products. That looks good. And let's just clarify, switch ion partners to produce the correct empirical formulas for the products. Next, we're going to balance the equation. So notice that on the right-hand side we have 2 hydroxides. So we need to put in a 2 in front of the lithium hydroxide. Now we have 2 lithium ions on the left, and so we will have to put 2 in front of lithium nitrate. Lastly, we're going to determine if one of the products is insoluble using the solubility table, which is shown on the bottom right. It says that alkali metal salts are soluble. So without even going further, I know that my lithium nitrate is soluble, right? Because lithium is an alkali metal. We go on to read that lead salts are insoluble. Of course, the exceptions would be when it's combined with the rules 1 and 2 above it. Lead nitrates, acetates, and perchlorates would be soluble. However, lead is combined with hydroxide and therefore is insoluble and will be a solid. And that completes the equation.